thank you for the invitation. It's very nice to be here. Let me say, first of all, this is joint work with Jack Thorne. And there is a paper. It's not on the archive, but it is on our websites, so you can find that if you're interested. OK, so let me start with some generalities. So let G over Q be a connected reductive group. Take G infinity to be the real points of this group. And inside here, I'll take a choice of a maximal compact mod center subgroup. And then I have the symmetric space, symmetric space associated with G, which will be this quotient G infinity modulo K infinity with its canonical Riemannian metric. So I want to define two integers that you can attach to this data. And my notation here follows notation in Borel and Pollock's book on cohomology of groups and of locally symmetric spaces. So I'll define L0 to be the rank of G infinity minus the rank of K infinity. I'll define Q0 to be 1/2 the dimension of the symmetric space as a real manifold minus L0. So these are both non-negative integers. It's not 100% obvious that Q0 is an integer, but it is. And to be clear, by rank, I mean the maximal dimension of any subtorus, split or otherwise. OK, now on the other hand, starting with this data, you can define these locally symmetric spaces, which have a lot of arithmetic interest. So for any K open compact in the finite adelic points of this group, I'll write yk for this associated locally symmetric space. And this is the sort of usual pithy definition, but it's always psychologically helpful to remember that this is just some disjoint union of finitely many quotients of this symmetric space. And so here these are lattices inside the real points of the derived group of G acting properly discontinuously. So I want to start off by talking about a basic principle of life with a bunch of examples. So this principle is that the integer L0 controls many aspects of the geometry and arithmetic of these YKs and of associated automorphic representations of G. Okay. So what are some examples of this principle? So example 1, I really do think this deserves to be called a principle. I have at least 6 examples that I can think of. So, and so example 1 is due to Harishchandra. And so this says that the group G infinity adjoint, which is a semi-simple group, has a discrete series if and only if this integer L0 is actually 0. So for this reason, L0 is sometimes called the defect of G infinity. It's sort of it measures the failure of G infinity to have discrete series in some qualitative sense. And furthermore, if these YKs are Schmor varieties, then necessarily L0 is also equal to 0. This is not an if and only if. There are groups that give rise to this situation without necessarily D infinity being Hermitian symmetric. But it is a necessary condition. OK. Example 2. These examples are going to get a little more conjectural as they go on. But part of the fun here is how these different conjectures interact with each other. So example 2, this is due to Bergeron and Venkatesh. And here the principle says that the cohomology of these spaces with integral coefficients, that this has large torsion subgroups. Or let me say has a large torsion subgroup. And by large, I mean large relative to the volume. And this should conjecturally be the case if and only if L0 is equal to 1. So SL3 over Q is an example of a group where L0 is equal to 1. OK? So example 3 is not conjectural. This is a fact. And so this is due to Burrell and Wallach. And also Zuckerman. So this says the following. So let L lambda C be an irreducible algebraic representation of the complex points of this group. And let pi be a cuspidal automorphic representation of G such that the Archimedean component pi infinity is tempered and cohomological of weight given by this local system. Or you might just say of weight lambda. I'll probably say that later. So then the pi part, and I'm not going to define this precisely, the pi part of this cohomology oops, sorry, I should put an actual variable here. This cohomology is non-zero only if n is contained in the interval from Q0 to Q0 plus L0. Note this interval is centered around 1/2 of the dimension of yk as a real manifold. And if you are in this interval, the dimension of this pi part is going to be proportional to a binomial coefficient. And so this is some integer m, which may be 0 if I don't choose capital K properly, for example. I'm allowing this to be 0. But this doesn't depend on n, is the point. So the dimensions of these pi parts as you vary n are proportional to a row, to the L0th row in Pascal's triangle. So that's pretty cool. I'm sorry? So this here, this is in non-negative integers, and it's independent of n. I'm thinking of pi as being fixed and n as moving around. So the pi part of the cohomology sort of looks different depending what degree you're in, at least from this qualitative point of view of its dimension.
How big is it compared to the volume?
I'm sorry?
How big is it compared to the volume once let k goes to get?
When L0 is positive, even the existence of regular algebraic cusp-forms becomes an extremely delicate question. So I'm not sure I have a good answer to that. I mean, if you fix a pi for which it's non-zero, then this will somehow, you can give this precisely in terms of the dimension of the space of fixed vectors.
Yeah.
And there's some complete description of this, but that reduces your question to a different question. Oh, this is backwards. Thank you. I guess that is the same as what you said, actually. That's right. Thanks very much. OK. So the main goal of this talk is to discuss a very interesting arithmetic enhancement, if you will, of this numerical result, which is conjectured by Venkatesh. And our work somehow consists of linking this conjecture of Venkatesh to some other examples of situations where this integer L0 plays a crucial role. So before I get to our work, let me mention two more examples of this principle. And so for the rest of the talk, the symbol pi will denote an object of this type. And I'm not going to say all these words every time. I'll just call it a tempered cusp form, but I'm only assuming that it's tempered at infinity. OK, so let pi be a tempered cohomological cusp form, as in the previous example. So then conjecturally, the order of vanishing at s equals 0 of this adjoint L function is exactly L0. And this is true in many cases. So this is true for any restriction of scalars of GLN. You can probably deduce it for classical groups in many instances, but this should be true in general. And this is somehow a purely Archimedean calculation. Again, this is something about the order of vanishing of some gamma factor. OK, example 5, which I can probably fit here. Are there any questions, by the way? I hope everyone doesn't already know all of this off the top of their head. Example 5, and this is due to Hida and Urban. And I'm not going to precisely define the objects involved here. So let curly x be the eigenvariety for G of level K. So this thing comes equipped with a weight map to some weight space, as in Hansen's talk. And this is just a disjoint union of p-adic polydisks, open polydisks. But it does depend in some mild way on the group and the level that you're working with. And so then I want to let little x and capital X be a point associated with, and I'm going to be a little loose here, a pi of this type. I guess I should say classical point. Then the conjecture, which Hida and Urban formulated, is that any irreducible component with x of this eigenvariety containing this point has dimension exactly equal to the dimension of the weight space. This is an equidimensional space, by the way, so this is a well-behaved quantity. The dimension of the weight space minus L0. So here's another sense in which L0 is a defect. These p-adic families tend to be small when L0 is positive, conjecturally, and the larger L0 is, the smaller they are relative to the possible space of weights they live over. Okay. Any questions about these examples? Okay, so what I actually want to talk about, so Venkatesh conjectures an arithmetic refinement, if you will, of this example 3 up here, which I'll formulate precisely in a moment. And our goal is relate Venkatesh's conjecture with example 5, and try to, well, I'll say try to prove his conjecture tensored with QP. So for the rest of the talk, well, I'm going to sort of subsequently make the group that I'm looking at more and more restrictive, and eventually it'll just be GLN of Q. But for now, I'll make it GLN of a number field. So now take G to be the restriction of scalars from some number field down to Q of GLN, where F has R1 real and R2 complex places. Sorry, this is the word. Places. So it's a fun exercise to calculate L0 in this instance. And when you do this, what you get is that L0 is equal to the floor of n minus 1 over 2 times R1 plus n minus 1 times R2. So this defect is 0 exactly when n is 2 and f is totally real. Okay. When n is 2, the defect is the number of non-real places. So in this setting, there's a basic conjecture due to Clauzel, which is that given pi, again, of this type, so regular algebraic cusp form on this group, given pi, there exists a rank n motive m pi over f. And to be precise, I should say it has coefficients in some number field E containing the field of Heck eigenvalues of pi, such that Frobenius eigenvalues on its various realizations match up with Heck eigenvalues. In the usual way. Okay. So I don't really know what a motive is. It turns out you can do stuff with them without knowing what they are. So later on, we'll switch to the p-adic realization of this motive, which does exist in many cases, unconditionally. But this conjecture is somehow really something that's supposed to take place with coefficients not in a local field, but with coefficients in this number field here. Okay. So I'm ready to state Venkatesh's conjecture, I think. Before I do, let me just say out loud that I have been writing this C here for a reason, because I can actually take incarnations of this module that have different coefficients sort of underlying them. So this representation makes perfectly good sense with an E here in particular, instead of with a C here. And so what I'm about to write will make sense. So conjecture. I should also say this is my interpretation of his conjecture. There's no written reference by Venkatesh for this yet. So anything I say is just my thoughts about this and should not be construed as something that he said. So I don't want to put words in his mouth. So his conjecture is that there is a canonical L0 dimensional vector space, which I'll call V pi, together with a canonical, and this is somehow the part that makes it a conjecture, is the fact that I'm insisting on canonicity here, with a canonical action of this exterior algebra over E of this vector space, on the pi part of this cohomology. And I have to be precise about what I mean by action, so I should say in our setup this is going to be degree lowering. And this action should make the latter, should make this cohomology module free of finite rank. As a graded module over this exterior algebra. Yeah, presumably. And furthermore, this is not quite satisfying because I haven't told you anything about v pi. I've just told you that there should be some vector space. But you can say what v pi should be. And furthermore, I'm just going to write this as v pi equals. But I guess I really should say v pi can conjecturally be taken to be the following thing. But this is just a fiddly detail. V pi should be the following X group. It should be an X1 in a category of mixed motives over OF with coefficients in E. And it should be X1 of the trivial motive by the add 0 motive of this m pi t-twisted once. So let me make some remarks on why you might believe something like this. The first sanity check would be to figure out whether or not this v pi actually has the correct dimension for this to be true, right? I know exactly what dimension this should have as a vector space if the conclusion of the first sentence is going to be true. And here you appeal to another conjecture, namely that Bloch and Kato have given this very precise conjecture for what the ranks of X groups like this should be in terms of orders of vanishings of L functions. And in fact, when you take the Bloch-Kato conjecture into consideration, the dimension of this is given precisely by example 4 that I wrote down earlier. So you get exactly that adjoint L value. So that's consistent. A more serious reason would be that this X group also appears conjecturally in Bailenson's description of the transcendental part of the adjoint L function at 0. And that transcendental part somehow comes by comparing two different rational structures on this tensor with the real numbers. One of them is given by this, and one of them is given by some other space. And on the other hand, comparing rational structures on cohomology groups in different degrees does give rise to periods of automorphic forms, which in some cases can actually be related to adjoint L values. So this conjecture is consistent with the appearance of adjoint L values on the Motivic side and on the automorphic side. And that can be made precise. I'm not going to make that precise. Are there any questions? Maybe more personally, let me just say I find this conjecture very intriguing because it's sort of the first hint that there might actually exist some kind of physical relationship between this thing, wherever it starts its life, and these symmetric spaces yk. Because remember, the yks are not going to be algebraic varieties if L0 is positive. So we certainly can't talk about their Étale cohomology or anything like that. But this makes it sort of seem like there might be a more loose kind of homotopy-ish relation between the two spaces, between the yks and whatever spaces actually give rise to the m pi's. But presumably this lives a little bit farther under the ocean than we can currently see. Okay. So what do we do? So now I'll restrict for simplicity to the case where f is q. And this is the context in which our paper is written. Although everything we do extends only with slight notational complexity to the case of an arbitrary f. Fix pi. I want to fix e as I did over here. Right, okay, fix pi and e. Okay, so we're going to work at a fixed prime, so let p be a prime. Such that the local component of pi at p has regular semi-simple Satake parameter. And let alpha.
What does that mean? That means
I'm sorry?
what does regular mean? Does the Satake parameter mean?
The set of eigenvalues is multiplicity free. Yeah. So let alpha be this row vector. Let this be a fixed ordering of, I'm going to say this in the most complicated possible way, I think, of the local Langlands correspondent of pi p normalized in the arithmetic fashion. So this is some Wedelin representation, and then I can evaluate it at a geometric Frobenius of p. So up to scaling, these eigenvalues are exactly the Satake parameter. So this assumption that the Satake parameter is regular semi-simple guarantees that there exist exactly n factorial such orderings. Is this okay? In the more familiar context, when n equals 2, and we're just dealing with classical holomorphic modular forms, choosing an ordering like this corresponds to choosing a root of the pth Heck polynomial, the usual polynomial x squared minus apx plus p to the k minus 1. In that case, alpha 1 would be exactly that root. Oh, I should have also said that I need to fix. So I already have E, and I'll fix E embedded inside C, and I'll fix an isomorphism of this with QP bar. And I'll switch back and forth between C and QP bar without particular comment. But our results do depend on your choice of this isomorphism. So we assume where do I say this? No, I don't actually want to say this yet. Okay. So let me say exactly what cohomology groups we want to talk about. So let n be the conductor. Of pi. And set hi pi to be the ith cohomology of this group gamma 1 n. So this is inside GLNZ. Over Q, I really don't gain much from working in the adelic setting in terms of setting up the cohomology, so I'm just going to switch to group cohomology. It's notationally simpler. Of L lambda. Oh, sorry. Then I want to fix. I do need to fix one more thing. some number field, some field L. I want to fix L in here, a finite extension of QP, which contains the subfield generated by E under isomorphism. Okay. Just think of this as a sufficiently large finite extension of QP. Okay, this will be my coefficient field for all the p-adic things I'm going to do. So I can also put an L here. That's legal. I want to define this. So we've taken this space at this particular level and tensored it over E with this p-adic field, this completion of E at a prime above P. And so we can also define a space that takes alpha into consideration. So this group here, this is the subgroup of elements of gamma 1n, which are upper triangular modulo P. Okay, this is not standard notation, but that's what it means. And so this has an action of UP operators on it at the prime P, and one can make good sense of the pi comma alpha part of this. And so it's a fact, although this takes a lot of ingredients to prove, it's a fact that the dimension in the top degrees here as L vector space is 1. So that integer m pi that I wrote down earlier is 1 when you set things up like this. This will play a surprisingly important role in our proof that this integer is 1. And I should say I'm really appealing to a whole lot of stuff under the hood here. I'm using the full power of new forms theory for GLN of a local field. I'm using exact calculations of these cohomology groups in terms of automorphic forms due to Burrell-Wallach and Franke Schwimmer and people like that. Lots of high-powered automorphic machinery is hiding behind this equality. So let's assume that this data alpha satisfies a small slope condition. And this is the part where the choice of embedding sneaks in, because the p-adic valuations of these numbers might change if you change your embedding. So then we construct a canonical point on an eigenvariety. I'll write x, but this x depends on pi and alpha. Inside this eigenvariety, this thing now has this tame level is this group gamma 1n. This is a classical point. It's a non-critical point, whatever that means. And I guess I should say this is an L point, this rigid space. Yeah, n is prime to p. Probably that phrase regular semisimple wouldn't make sense. I mean, stock A parameters wouldn't parameterize it. Yeah, that was an oversight on my part, though. I'm assuming that the conductor of pi is prime to p. So what's next? So this eigenvariety is some locally ringed space, and so I can define the local ring at this point, and I can take its completion. And I can also define a local ring of the associated point and weight space. And in our setup, these are both complete local Noetherian L algebras. We build L into the setup of the eigenvariety. And this, in this situation, is very simple. This is non-canonically just a power series ring in n variables over L. And this is something to which that earlier dimension conjecture of Hida and Urban applies. So this ring is conjecturally equidimensional of dimension n minus L0. Okay. So in this setting, so Hida and Urban conjecture. This ring, Tx, is equidimensional of dimension n minus L0. And it's another fun exercise to check that n minus L0 is 1 plus the floor of n over 2. Oh, let me say, this is true if L0 is equal to 0, in which case it's a classical theorem. In this case, it's due to Stevens. And this is the proper noun that I put here is related to the construction of the eigenvariety that we're using. There are different constructions of eigenvarieties due to different people. Ours go through the overconvergent cohomology groups of Ash and Stevens. And this is also true if L0 is 1. In this case, it's due to Hida if alpha is ordinary. And I proved it in my thesis in general. So what I'm about to say will be unconditional if L0 is 1. So let me just mention one more ingredient in this puzzle, and then I'll tell you a theorem. So we also define a finite faithful Tx module Hx, and this again is secretly some graded module which comes as a bunch of cohomology groups. And this is a module of p-adic automorphic forms. This has the property that in the top degree, so this is naturally a lambda module, since Tx is a lambda algebra. If I tensor this over lambda with its residue field, this is actually canonically this classical cohomology module in top degree. Okay. So here's the theorem. So this theorem assumes that the dimension conjecture above is true. At this point that I've defined. So then a whole bunch of stuff happens. So first of all, this module of p-adic automorphic forms vanishes if you're not in the top degree. And if you are in the top degree, and I'm going to introduce special notation for this, since I'm going to refer to it a couple more times, this module of top degree automorphic forms is free of rank 1. Over the Heck algebra acting on it. Okay, part B says that there exist canonical isomorphisms of the classical cohomologies that I defined earlier. Where did they go? Of these in lower degrees, which turn out to actually be recoverable from this, but not in an entirely trivial way. This is a Tor group. And this is for all I greater than or equal to 0. So when I is 0, this is exactly this isomorphism that I claimed up here. Oh, sorry, this should be pi alpha. But in general, nothing as clean as this will be true without the vanishing in part A. So you can actually recover all these cohomologies from this one module of p-adic automorphic forms. The third thing we prove is that the map from this weight ring to the Heck ring is surjective. And the Heck ring Tx is a complete intersection. There's a final part to this theorem, which actually relates it back to this conjecture of Venkatesh. So part D is the following. So set Vx to be the kernel of the surjective map from part C. But I'm going to tensor this now over lambda with L. And so this is an L0 dimensional vector space over L by part C. So then there exists a canonical degree lowering action. Well, I'll just say action of this exterior algebra on this module and by the dimensions of these, which I've already remarked upon, this forces this to be, well, it doesn't quite force this, but one deduces that the latter is free of rank 1. As a graded module. questions about the statement of this result?
Can you tell us the definition of H?
I can tell you something about how it's defined. I don't know if I want to write it precisely, but these eigenvarieties of Ash-Stevens are constructed by looking at cohomology of certain modules of distributions, just like in Hansen's talk. And so you choose some small alphanoid in the weight space containing the weight you're interested in. You look at the cohomology of a suitable local system of distributions of that weight over that little disk. And then this will have some slope decomposition if you make your disk small enough. And then you can complete it at the maximal ideal in the Heck algebra corresponding to this point, x. And that's the formal definition. And it turns out this is independent of the choice of disk and slope decomposition. So those modules I just mentioned can actually be sheafified over the eigenvariety. So this is the fiber of that sheaf at this point. I don't think I have time to say very much about the proof here. But let me just mention, so a key point in the proof is that in the setup there exists a canonical spectral sequence which calculates these modules of classical automorphic forms that I mentioned earlier in terms of the totality of these modules of p-adic automorphic forms. So this is true whether or not the dimension conjecture holds. And then one starts by showing that the dimension conjecture forces these to vanish outside a single degree. And then this degenerates to the isomorphism that I claimed in part B. And then one can independently prove, using the fact that in top degree this is of rank 1, well, that implies that this is, in top degree, is generated by one element over lambda, by Nakayama. And by construction, this is a faithful module when you add it up in all degrees. So if it only is non-zero in 1 degree, then it's faithful in that degree. And from there, it's actually pretty easy to deduce that Tx really is a quotient of lambda, and that Hx is free of rank 1 over Tx. And we also use this fact, which seems to not be used very often, that if you have a ring R, a commutative ring, and two commutative R algebras, A and B, then Tor R, the graded ring Tor R of A comma B, well, sorry, I gave the game away. The graded module Tor R A comma B is in fact a graded ring, a skew commutative graded ring.
First thing you said was something, you saw something vanished outside 1 degree.
These p-adic cohomologies here.
So the first thing is you see they vanish outside
The top degree, yeah.
So where did that come from?
So that's sort of the key point, and that comes from a commutative algebra lemma that says that they can be calculated as the cohomology of some perfect complex of length L0. There's a sort of general lemma, and this was observed independently by Caligari-Garrity and myself, sort of in the context of problems like this, that if you have a perfect complex of length L0 and its cohomology has support which is equidimensional of dimension, codimension L0 over the base ring, then its cohomology is concentrated in 1 degree. That's the key point. This is a very special case of something that's sometimes called the intersection conjecture in commutative algebra. But in this case, it's easy because the base ring is regular. OK, so this is maybe not so satisfying because this space Vx here doesn't look related at all to the V pi that I defined earlier. And so let me just end by saying one word about what V pi really is. And I'll try to say this in not too precise a manner. So assuming a certain R equals T type conjecture, show that the space Vx is actually canonically identified with the p-adic incarnation of the module V pi that I defined earlier. So this is canonically, it's a canonical Blockato H1F, and then here I have add 0 rho pi Tate twisted once. And if we are in a motivic paradise, then this is V pi tensored over E with L. So this is conjectures piled on top of conjectures, but I think the structure here is maybe still interesting nonetheless. So I should say we don't know how to prove this R equals T conjecture. You could prove it in some cases if you knew local global compatibility at P for the Galois representations into this. So I guess I can put an X here. We have some conjectural description of this as a Galois deformation ring, parametrizing Galois representations which are trianguline at P, not crystalline, not geometric even. But nonetheless, when you try to describe the tangent space to this Galois deformation problem, you do see H1Fs showing up, and that's somehow the key link here. Okay, I don't think I have very much more to say. Are there any questions?